Good evening, students. So yesterday we discussed about the hybridization in methane, that is SP3 hybridization. We discussed yesterday. Today we will discuss the same SP3 hybridization in in the case of ethane. We will see ethane. So here SP3 hybridization in ethane. Ethane is CH3, and generally we write it like this, expanding formula like this we write, but in general the bonding in the ethane is not like this. Here if you see, everywhere is 90 degrees, bond angle is 90 degrees, but experimentally it was found that the bond angle in ethane is 109.5 degrees, like methane. Yesterday in the previous class we discussed about the bonding in methane using sp3 hybridization, where we found that the bond angle is 109.5 degrees. You can see that video. I will give the description link in the description of this video. So here suppose if we assume this is C1 and C2, but both are same, actually both are same. For our convenience we will assume that this is C1, this is C2. If we take C1, its atomic number is 6 and electronic configuration is 1s2, 2s2, 2p2. So in the ground state, for this carbon I am writing, same applies to this carbon also. This carbon I am writing, same applies to this carbon. That means this carbon also happens like this, and this carbon also will happen like this two times. This carbon one time, this carbon one time, and both will be combined. So here ground state, this 2s is like this we write, and 2p is like 3 orbitals subshells. So here in 2s we have 2 electrons, in 2p we have 2 electrons like this, and in the excited state this electron in the 2s orbital will jump from 2s to 2p like this electron will jump here like this, and this is sp3, that means one s, 3 p orbitals. This is s orbital, 2s orbital, 2px, 2py, 2pz orbital. Now in sp3 hybrid orbital hybridization, this s orbital and 3p orbitals combine together to form 4 new sp3 hybrid orbitals, and they are arranged in the space like this. In the space they will arrange like this, like this. So here everything is tetrahedral geometry, all the angles are same. Generally this is above, this is on the plane, above the plane, below the plane, like that I will write the structure. And this is for this carbon, and for this carbon also 4 new orbitals will form, and they will be arranged like this, like this, like this, like this. So like this, this is one carbon, this is one carbon, this carbon and this carbon. If you see here 90 degrees you are able to see, but here if you see this, because this is tetrahedral geometry, the angle between these orbitals are 109.5 degrees, 109.5 degrees. Here also same, 109.5 degrees. Here also same, here also same, and here also same. This is one carbon, this is one carbon, and here these 4 orbitals, 4 electrons are available. Here electron, here electron, here electron, and here electron. This orbital, here electron. And for this carbon also 4 new orbitals will form, and there also 4 electrons will be there. So this electron, this electron, this electron, and this carbon in between, this axial bond is formed between this sp3 hybrid orbital, this sp3 hybrid orbital, and this is called sigma bond. Sigma bond. So here on this carbon 3 hydrogens are available, on this carbon 3 hydrogens are available. Hydrogen means this is 1s1, and s means spherical shape. So in this spherical shape 1 electron is available. So that one electron will form bond like this. This is hydrogen, form bond like this. This is hydrogen, form bond like this. Here also on this carbon also same, 3 hydrogens forms 3 bonds like this. It will form. Now if you write the actual structure for this orbitals, here hydrogen is there, here this is below the plane, inside this is plane, so inside the plane with the dotted bonds one hydrogen is available like this, and this is above the plane wedge bond, and this is sigma bond here, and this is below the plane, this is above the plane wedge bond, and this is on the plane, on the paper. So this bond is on the paper, this bond is on the paper, this bond is on the paper. So that is the shape. This dotted bond means inside the paper. This is wedge bond means above the plane, above the paper. So that is above the, like this, above the plane. Okay. Here also bond angle is 109.5 degrees. Here also same 109.5 degrees. Here also same. Here also same. All the bond angles wherever you see 3 atoms, whether carbon hydrogen or carbon hydrogen, whatever you see, all the angles are 109.5 degrees. And here also this carbon is having geometry, that is tetrahedral geometry, and here also that carbon is having tetrahedral geometry. So this carbon also tetrahedral geometry, this carbon also tetrahedral geometry. Like that in ethane both the carbons are having tetrahedral geometry. So this is the bonding in ethane. Methane we have seen, ethane this is the bonding. So after this, regarding SP2 hybridization, here the example is ethene, and ethene structure is CH2 double bond CH2, and we write that like this, CH double bond CH. For our convenience, if we write like this is C1, this is C2, both carbons are same, wherever carbons are there they are all same in nature, properties, everything. So here if we write for this C1, that C1 ground state electronic configuration is same like this one, 2s2 2p2, here 2 electrons, here 1 electron. In excited state means before going to form a bond, electrons will be excited, that means acquire energy. Excited means acquire energy. By acquiring energy, this electron will jump from 2s orbital to 2pz orbital. Here this electron is nothing but this one, that means excited state. Now it is SP2 hybridization. SP2 hybridization means one s orbital and 2 p orbitals up to here only. In SP3 total 4 orbitals, SP3 hybrid orbital, that means 3 p orbitals. But here in SP2 hybridization, one s orbital, 2 p orbitals like this, and this pz orbital is as such it will be there on the plane of the molecule, that I will tell you later. So here 3 one s orbital, 2 p orbitals, total 3 orbitals combined for this one carbon, 3 p orbitals combined to form 3 new sp2 hybrid orbitals, and they will be arranged in the space like this. So this is one sp2 hybrid orbital, and this is another sp2 hybrid orbital, and another third one is this is another sp2 hybrid orbital. 3 sp2 hybrid orbitals will form and they will be arranged in the space like this. That is for one carbon, that is for this carbon. And for another carbon also, following this total, the same 3 new sp2 hybrid orbitals will form and they will be arranged in the space as such like this. This is for this carbon. one is that one is this one is this one. So here you can see this carbon and this carbon, this sp2 hybrid orbital, this sp2 hybrid orbital, for these two carbons are bonded using these electrons. 3 sp2 hybrid orbital, 3 electrons are there. Here one electron, here one electron, here one electron. For this carbon also, here one electron, here one electron, here electron. So these two carbons, one is for this carbon, another one for this carbon, bonded to form a sigma bond. Sigma bond. And here 4 hydrogens are available. Like here I told you, hydrogen means 1s1 and it contains s orbital with 1 electron into it, and that will form bond like this. Here also bond like this. Here also bond like this. Here also bond like this. These 4 hydrogens, 4 bonds are formed. Now here if you see, an unhybridized pz orbital is available. That orbital is situated on this plane. This, if you see how it is looking like, here if we write it is like this, a triangle. If we combine this triangle, here also a triangle. If we combine this, a triangle. So that means this carbon is a triangular structure. This carbon is also a triangular structure. That means trigonal structure. So it is plane molecule. This carbon is also on the paper. This carbon also means this bond is also paper. This bond also paper. This bond also paper. That means this carbon also on the paper. This carbon also on the paper. So this is a planar molecule. Planar and trigonal structure. Trigonal structure. But here this carbon is tetrahedral structure. So, but in sp2 hybridization, this carbon is a planar structure, planar triangular structure. Okay. Now to this planar structure, this unhybridized orbital will be situated above the plane like this and below the plane like this. That means like this. This pen I kept how perpendicular to the plane of the paper, like that this orbital is exactly perpendicular to the plane of the paper. So here on the air, in the space, this lobe will be there. In that, one electron here already there. That electron is there here for one carbon. For this carbon also same happens. Here electron is there. So these two are overlapped above and below, because it is electron density. So it is, electron means electron cloud. So it is overlapped. This is called lateral overlap, and this bond is called pi bond. So lateral overlap using the pz orbitals is called pi bond, and axial overlap using the sp2 hybrid orbitals, that is sigma bond. So one sigma bond, second sigma bond, third sigma bond, fourth sigma bond, fifth sigma bond. That means 5 sigma bonds are there. 5 sigma bonds are there, and one pi bond is there in ethene. So if we write this one, so this carbon is this one, this carbon is this one, and this bond is this below bond, sigma bond. This bond is this above bond, pi bond, and this bond is this hydrogen, this bond is this hydrogen, this bond is this hydrogen. So like that, totally bonds are formed, and bond angle means here triangle means bond angle is this orbital to this orbital bond angle is 120 degrees, and this is also 120 degrees. This is also 120 degrees. Triangle means all the angles are same. This angle, all the angles are same. This one. Total everywhere you take the angle is 120 degrees. That's why it is called trigonal structure, and all the bonds are on the paper. So it is all the bonds are on the paper, so it is planar structure. So this is the structure of ethene molecule using sp2 hybridization. And regarding sp hybridization, we will discuss in the next video. Okay, thank you.